There we go. Let me see. The white pen works. Okay. So that's it. So we will start with an exercise from last time, and that is two lines. So we didn't have time to discuss this on Monday, so we are doing it now. So to prove that two lines intersect and find the coordinates of the intersection point. That would come at the same time, at the same moment. The first thing, of course, we could see that the direction vectors, that the two direction vectors, the direction vector of the first line and the direction vector of the second line, something is happening there. Okay, now it's all right. They are not parallel. We see -1, 5, 2 is not proportional to the vector 2, -2, 3, which was the problem with vector collinearity or parallelity. Many of you went against my warning. You try to do something with the scalar product or with even the vector product, that horror of horrors, when all you had to do is check the proportion. So many of you went astray. I do suspect that would be those people who switch on their computer, write their name, and then just get lost. But that's probably your problem. Yes, it is possible to say that, yes, if two vectors are collinear, then their vector product would be 0, but it's a 0 vector. So that means you need to check that all coordinates are zeros, not just one coordinate or not just add everything together, because they are completely different things. So this is the easiest way of checking that two vectors are or are not collinear. Nothing else. Everything else will be just confusion. And so we see that these two lines, first of all, they are not parallel. The vectors are not collinear, which means these two lines are not parallel and they cannot coincide. So either they do have a common point or they do not. Either they intersect or they do not have any common points. So proving that these two lines intersect actually can be done basically only by finding that intersection point, proving that this intersection point exists. So there are several ways of doing this. If we have the canonical equations for both lines, then we could do it, for instance, like this. Take the xy coordinates from one line, xy coordinates from the other line. So we have two equations and solve this system. Find those xy coordinates that the two lines have in common and then check. But without checking, nothing happens. We really have to check this thing, and that will be, we need to check that with these xy values, the z value for each line is also the same, because we might have the same xy for some point on the two lines, but the z value for each of these lines is different. So which would mean that these lines pass each other by. They are skew lines then. So in principle, we need to find the coordinates of a point. Let's call it P, with coordinates x, y, z, that would fit into both equations. The thing is that this point has to fit into both equations. We can start finding this point using only part, so xy from one and xy from the other, but then we need to check the z value as well. So that would be one possible approach. Let's try it. So let's take from the first, so this will be from the first line, we get 5 times x minus 1 equals minus y minus 2. Remember that we can cross multiply a proportion. And then from the second line, we would have minus 2 times x minus 2 equals 2 times y minus 5. That's from the second line. I'm simply taking the first two coordinates and performing, the property of proportion. If you multiply diagonally, then of course the two products should be equal. So we have 5x minus y moving to the other side becomes plus y. And here we have minus 5 going to the right-hand side becomes plus 5 minus 2, we get plus 2. And on the left, we have minus 2x. 2y goes to the left, minus 2y. On the right, we have minus 4 from the left. Now, plus 4 from the left goes to the right, becomes minus 4. And 2 times minus 5 is minus 10. So we have a comparatively simple system. 5x plus y equals 7. And let's divide everything by minus 2 in the second equation. We would have x plus 2 equals, dividing minus 14 divided by minus 2 is also 7. Now this is something quite interesting, because if we subtract one equation from the other, we actually get that x is 0 and y is 7 for this point. So if x is 0, y is 7, then we should now try and see what happens with the equations of the two lines when x is 0 and y is 7. We would get 0 minus 1 over minus 1 equals 7 minus 2 over 5 equals z plus 4 over 2. We don't know what z is. And from the second line, this will be the first one. And for the second line, trying in these values, 0 minus 2 over 2 equals 7 minus 5 over minus 2 equals z minus 1 over 3. So we see that here we have the ratio, it's 1. This ratio, 5 over 5, is 1, equals z plus 4 over 2. We see that from this, we see that z should be minus 2. If z is minus 2, then we have 2 over 2 is 1. From the second line, we get minus 1, we get minus 1, 2 over minus 2. And of course, it has to be equal to z minus 2 over 3. And from this, we see that in principle, we should have z value minus 2. Or another possibility, we got the z value from the first line. Check that the same z value also works in the second line. Also works in the second line. We see that minus 3 over 3 will also be then minus 3. So we have checked the z value. The point is, the solution, as you start solving these systems of equations for two lines, trying to find the intersection point, everything that matters is that you check in all three coordinates. The same goes, for example, for the collinearity of two vectors. You generally found the possible values of parameter in the quiz, in the second test, from two coordinates. But what you missed, most of you, was that you have to check in the third coordinate as well. Perhaps you find some m values. Actually, there were two m values to be found because it was a quadratic equation. Many people lost the second value at all, which was the good one, and they didn't check that the one they found was the wrong one, actually. So, in fact, we have to make sure we find all the possibilities from whatever equation we get. But the most important part is they need to be checked so that, yes, we verify this value of parameter works in all three coordinates. That was the main error with parallelity of vectors. The task with parallelity of vectors. You had to find the parameter k or t or p or m with which the two vectors are parallel. It had to be checked, verified that it works in all three coordinates, in all three ratios. Just like with this, we find xy using the first two coordinates, only xy coordinates, but then we need to check that the third coordinate actually works in both lines. And then, of course, writing down the answer. So the intersection point would be, as we can see, 0, 7, and minus 2. Those are the coordinates. approximates. This is one approach from canonical equations. Another possible approach is if you have the parametric equations of the two lines. If you have the parametric equations of the two lines, I will now erase this. So those of you who are really late, take a quick screenshot of this. Press print screen, take a screenshot. I will wait a few seconds because then I will actually clear off this writing so that I free up some space for my second approach, second method. Okay, I'm doing it now. And the second possible approach would be write the parametric equations. So the first line would be x equals 1 minus 1t, y equals 2 plus 5t. Remember that in the parametric equations, we use exactly the same values, the same points, the same numbers. So minus 4 plus 2t. So the point on the first line is 1, 2, minus 4, and its direction vector, minus 1, 5, 2, makes the coefficients for the parameter t. So that would be for the first line. And for the second line, we have x equals 2 plus 2. The problem is, this is one problem, the parameter value should not be the same for both lines, because the parameter simply tells us how many direction vector steps we need to take to the specific point. So in principle, if the point is the same, still we start from different places on both lines, and the number of steps would be different. So we need to name the parameter differently. It's a different parameter for each line. There's no rule that states that for both lines the t value has to be the same, because we start counting from different points, from different places. So the parameter basically is independent. The parameter on one line is independent from the parameter on the other line. We will try to somehow reconcile them to find some kind of connection, but in general, for general points, the parameters are not connected. 5 minus 2, s is the new parameter then. Answer is 1 plus 3s. So now we have basically one set of parametric equations for line 1, another set for line 2, with a different name for the parameter, because they are mutually independent. And so now we need to find the point for P. X values should be the same in both lines. Y values should be the same in both lines. And Z values should be the same in both lines. So I'm writing 1 minus T should be equal to 2 plus 2S. 2 plus 5t should be equal to 5 minus 2s, and minus 4 plus 2t for z should be the same as 1 plus 3s. Now we need to solve, interestingly, a system of 3 equations, but only 2 variables. Which means that we can, for example, find the 2 variables from 2 equations, but we must check them in the third equation. Again, the same thing. We need to check that the same values of s and t work in all 3 coordinates, in all three equations. So it looks like, in this case, okay, I lost something, I think. Right now. So we have to, it looks like these 2 equations would be very good for finding t, because you see, if you add the first and the second equation without changing anything, the s parameter will disappear, it will cancel out. So I have 3 plus 4t when I add them equals 7, and 2s minus 2s disappears. So we have 4t equals 4, t is 1. And then when t is 1, From there, we can actually get the second parameter. We can get the parameter s. That would be 1 minus 1 equals 2 plus 2s. That's from the first equation, from the first coordinate, which means 2s equals 0 minus 2. That's minus 2. And s equals minus 1. So these two coordinates, these two numbers, t is 1, s is minus 1, actually work for the first two equations because we found them from the first and the second equation by addition. Again, it's not stated it has to be the first and the second. It could be the first and third, or second and third. It depends on, well, what you find convenient. Any two equations that you can find convenient. But now I'm putting t is 1, s is minus 1 into the third equation to check. So minus 4 plus 2 times 1 should be the same as 1 plus 3 times minus 1. We see that minus 4 plus 2 is minus 2, and on the right-hand side, 1 plus minus 3 is also minus 2. That's it. So yes, it works in the third equation. We have checked. We have found these from the first two equations, and we have checked it in the third equation. So the point P would happen, the intersection would happen if T is 1 and S is minus 1. It doesn't matter which you use because the point will be the same. So I take T is 1, put it into the first line in the first equation, I get my point P. Similarly, I can take S is minus 1 and put it into the second equation. I still get the same point, the same coordinates, because that was how this system was actually set up. So that, yes, we get the same point. And so we see if T is 1, then from the first equation, if t is 1, we get 1 minus 1 is 0. The first coordinate is 0. 2 plus 5 is 7, same point. And of course, minus 4 plus 2, this is something that we already have here, by the way, is minus 2. Same point. So it's up to you. I would probably guess that using the canonical equations directly might be your preference. However, if you would prefer to use parametric equations, remember that each line basically uses a different parameter. The parameters are not directly connected, different parameters. So here we could use parameter t, and here we would use parameter s. And if I have some other line to analyze with these two, I would still use another parameter. So I would invent a different name for that parameter. So finding the coordinates of the intersection point means basically I must have these equations where both lines are satisfied by the same set of values x, y, z. Which means, yes, indeed, you must check all three coordinates, that everything fits. Now, lines and planes finally. When we are looking at lines and planes, we have generally, a line has a direction vector. For the line, we generally have a vector m, n, and p with the canonical equations. And for the plane, we generally have the normal vector. That's A, B, C. That's, let's say, the standard situation that we have. That for the line, we have the direction vector, and for the plane, we have the normal vector. So interestingly, how should we deal with this situation? So the angle between vectors, of course, the angles in space in analytical geometry are found as angles between vectors. So this is the same thing, the normal vector of the plane, the direction vector of the line. Now the situation, now we need to see what it looks like. It looks like something like this. Now, it might be slightly different, slightly difficult to copy, but do try to sketch, because actually things going through your hand make sense. Actually, as I discovered, many of you, if not everybody, just watch the lecture but don't take notes. I would say that's a mistake, because no matter how many times you watch, if you don't try writing things down and doing things by yourselves, it won't work. It won't stay in your head. There's no way. Every old teacher, and I am an old teacher, every old teacher would say the same thing, that knowledge gets into your mind through your hand. And that's why the current generations who are not used to writing things down, not even on a computer, but writing with a pencil or a pen, have weaker memory and let's say not as good a mind, because when a small child learns to write using his fingers, using pens, pencils, and everything, it actually develops the mind, and it stays with you for your whole life. It stays with you for your whole life. So your motor skills with your fingers, even when you simply copy things that we talk about, helps your mind. And therefore, I would seriously advise you to take notes and try to solve things with me, not just watch how I do it. And so, see, we have this direction vector of the line, the green one, the direction vector of the line, the green one in my diagram, and we have the normal vector, the heavy black, n vector of the plane. I will try to get a darker pen in order to write this. Is the vector s, the direction vector of the line, and this is the vector of the direction vector, the normal vector of the plane. So yes, as an angle between two vectors, we can find the angle between these two vectors. Is that the angle between the line and the plane? Well, no, not really. It's this angle or this angle, sometimes the obtuse angle, but then we will solve the problem by making the cosine positive. And it was astonishing how many people did not get the angle between vectors right. But I suspect those people are not present here today, so I will not say what I think of those. But you see, the actual angle between the line and the plane is this. Remember that an angle between a line and the plane is, in fact, the angle between the line and its projection in the plane. So if we project the line perpendicularly to the plane, then the actual angle between the line and the plane is defined as this angle, the angle phi, degrees or no degrees, but evidently, when we find the angle between these two vectors, we actually find the angle theta. We are not finding the angle phi between the line and the plane, really. So the angle theta is the angle between the two vectors, or rather the two lines containing these vectors, because yes, we might get an obtuse vector accidentally if the directions of these vectors are, for example, like this or like this. It depends. We don't know. When we have the abstract vectors given by numbers, we don't really know in space in 3 dimensions. It's not obvious whether the angle between these vectors is acute or obtuse. And therefore, it could be accidentally obtuse. So anyway, if this angle is acute, we take only the acute version. We take this acute angle. So we generally take the acute angle less than 90 degrees. Then the angle between line and plane is the other angle in this right triangle that we have here. We have here a right triangle. This is a right triangle. And in a right triangle, you know the sum of the two acute angles is actually 90 degrees. So if we find that theta angle, we can take 90 degrees minus theta. It is the angle between line and plane. So that's one thing. That's the difference. When we find the angle between two lines, you find the angle between the vectors directly, and that's it. When you find the angle between two planes, you find the angle between the two normal vectors, and that's it. But when you are finding the angle between two different objects, line and plane, the nature of those vectors is different. One is normal and the other is direction. So that's the reason for our problems, perhaps. So the cosine of that angle would be this. However, remember that cosine tends to be negative sometimes. To get the acute angle, the cosine has to be positive. So if necessary, we take the absolute value against something that you theoretically knew, but you lost it completely in the unit test about vectors. So we take the modulus of that value in case the vector scalar product was negative. We took the absolute value to make sure that the cosine is positive, because the cosine of these supplementary angles, the cosines are opposite numbers. The cosines of these supplementary angles are opposite numbers. Now, next, we have two approaches. First option, remember that in the right triangle, what is cosine for one angle, acute angle, is actually sine of the other angle. The cosine is adjacent side divided by hypotenuse, and the sine is opposite side divided by hypotenuse, right, from the right triangles, which means what is adjacent to one angle is actually opposite to the other angle. What is sine for one is cosine for the other. So in principle, this cosine is actually the sine of the angle that we need. And therefore, we could simply remember that the angle between a line and the plane is found as the angle between two vectors, only not the cosine, but the sine of this angle. So one approach would be we do the normal thing that we are used to doing when we are finding the angle between two vectors, only we understand that this will be the sine, not the cosine of the angle we seek. That's one option. So because it's not between two lines, not between two planes, but between line and the plane, different objects. So things change a little bit. The second option is you simply find the angle theta, and then you take, okay, 90 degrees minus that, because in geometry we mostly think in degrees. Radians are kept for trigonometry, for the algebra parts. So subtract from the right angle and you get the angle that you need. So the angle between a line and the plane has this specific situation, for you. Okay, let's have special cases. In this case, suppose we have a line that is parallel to the plane. So we can sketch, or you can sketch a plane. The plane has a normal vector n, as you see, the orange one, and then we have a line that is parallel to this plane, which means its direction vector is parallel to the plane, and that means the direction vector is perpendicular to the normal vector. This is where you need to sketch. So if we are exploring parallelity between a line and a plane, we have to understand that the direction vector of the line and the normal vector of the plane have to be perpendicular, because the line is parallel to the plane. That is, it is perpendicular to the normal vector of this plane. And so sketching is necessary if you want to understand what is going on. So in a situation like this, I will expect a sketch in your homework, in your unit test, in your midterm examination. So the line is parallel to the plane if and only if the two main vectors, direction of line and normal of plane, are perpendicular. So this means, yes, this means the scalar product of these two vectors equals 0. I feel compelled to remind you that the scalar product is always denoted by a dot. That's the dot product. If you mark the wrong sign, that's a mistake. I saw a lot of that in the unit test. People are simply not paying attention. And the next is parallelity, or rather perpendicularity of the line and the plane. So if a line is perpendicular to the plane, again, what is necessary is a sketch. We should make a sketch. So the plane, if the line is perpendicular to this plane, supposed to be a line, then its direction vector and the normal vector of the plane, of course, will be parallel. So perpendicularity, a line is perpendicular if the vectors are parallel. See how strange this is. Between two lines, everything is easy and simple. Between two planes, everything is easy and simple. As soon as we get a line and a plane, everything gets turned upside down. For the angle, we have the sine and not the cosine. For parallelity, we check perpendicularity of vectors. For perpendicularity of line and plane, we check parallelity of those vectors. So that is a little bit strange, but yes, this is how things happen. This is how things happen. And please be reminded one more time. I'm reminding you that parallelity of vectors is checked in a standard way by this proportion, by proportionality of the corresponding coordinates, not by dot product, not by cross product. It would involve too much difficulty. I think I saw one person who was checking by the cross product. No, not exactly sure. Not even exactly sure that they did it to the end. I think they stopped, found one coordinate from one coordinate, and then they didn't check further on. Don't remember exactly. So this is something that is difficult to do, messy, complicated, and generally too confusing for you. Use the simple ways. I always try to give you the simplest method in the lecture, the simplest method that we have in the lecture. So all those who complain that I didn't understand anything, I had to look elsewhere, then please be advised that elsewhere it's probably more complicated and I will not accept it without explanations. Now I need to move on to the next slide. Intersection of a line and a plane. We just did intersection of two lines at the beginning of this lecture. So now intersection between a line and a plane. So that means that we have, I think I don't have a picture here, so I have to sketch anyway. We have a line and a plane, and this line intersects the plane. So we have the plane, we have the line. The line is given by a canonical equation. The plane is given by the normal vector equation, the standard equation. We need to find the intersection point. So in principle, yes, it would be possible to solve a horrible system of equations. So we could have this x minus x0 over m, y minus y0 over n, z minus z0 over p, and ax plus by plus cz plus d equals 0, which means we have three unknowns. Remember that all the x0, y0, z0, mnp, abcd are numbers. We still have three unknowns. We have unknown x, unknown y, unknown z to look for the common point. And we have, yes, we do have three equations. See, you have three equality signs. which means you have 3 equations. It looks like 2 equations, but remember that the line has canonical equations, plural, 2 of them. We could try to solve this as a system, write it as a system in 3 variables. It's linear. You could simplify, and you could use methods of linear algebra to solve this system. Perfectly, that's fine. But it's much easier if you write the equations of the line in the parametric form. Again, don't forget, we use exactly the same numbers, x0, y0, z0, m and p, as coefficients at t. So we have expressed all the coordinates of points on the line x, y, z using a single parameter t. And now, of course, we are looking for the point for which these coordinates on the line, coordinates of the point on the line, also fit into the plane equation. So what we do is we substitute these parametric equations into the equation of the plane. So we have this equation of the plane, but instead of x, y, z here, instead of x, y, z, we actually substitute the parametric expressions. See, this is x from the line, this is y from the line, this is z from the line. And now we have many constants, but only one unknown, that is t. Which means when we solve this, we find the value of t for which this is true. It means that for that value of t, the coordinates of the point on the line actually also fit into the equation of the plane. So that would be this intersection point. I could call it, for instance, M. And in this situation, then when we solve for t, then we use the t value into the equation of the line to find the coordinates of this intersection point. We will have examples. So in principle, what we do is write the equations of the line in the parametric form, which is the best option because that way we are only using one unknown, that is t, one variable t. The rest is numbers. So the equation of the plane then would be easy to solve for this value of t. Let's have a look at an example. Suppose we have a line and a plane. And let's consider 2 things. Find the intersection point and find the angle between these 2. So what we have is, it's always a good idea to make a sketch just to remind you what these things look like. And then you could also remember that the angle evidently between the line and the plane will not be the angle between the normal vector and the direction vector of these 2 objects. So the normal vector was something that I generally depicted, I think, in orange. So this is the normal vector of the plane, and then we have the direction vector, which is generally, I think, depicted in green. Let's do it in green. The direction vector of the line, and so that would be for the angle later on. And we see that yes, the angle between these 2 will not be this angle. It will be this complementary angle. This is the complementary angle. Complementary angle is the angle that adds until we reach 90 degrees, and supplementary angle is that adds to the given angle until we reach 180 degrees. It's always very confusing with this terminology. People do confuse them. And so, finding the intersection point, I will write the line parametrically, x equals 1 minus 2t, or we can actually write the point is 1, 0, 3 from the equation of the line. The vector is minus 2, so minus 2t, 1 that is plus simply t, and 0 that would be plus nothing. So these are the parametric equations of the line. And now we put them into the equation of the plane. So we have 2 times x. X is 1 minus 2t minus 3 times.
How you get y equal to 0 plus t? It's y.
Because the point through which the line passes is 1, 0, 3. We see there's nothing subtracted from 0, from 1.
Okay.
We can say y minus 0. Because
Okay.
these numbers x0, y0, z0 are the coordinates of the point,
Okay.
since
Okay.
y0 is 0, there's nothing there, it's 0. Okay, so 3, y is t, so 3t only, and plus 10 times z, z is just 3, and minus 4. This is something that people sometimes forget. They forget this d constant. It's a very common error, simply forgetting the d constant. Not because you don't know, but because you copy things, and okay, z is finished, equals 0. But d is easily forgotten, but we should not. And so we solve this. 2 minus 4t minus 3t plus 30 minus 4 equals 0. And so we have minus 7t, combining these, and then we have uh, 2 plus 30. 32 minus 4 is 28, which means t is, as we can see, equal to 4. And so the intersection point, from that line and from t is 4, the intersection point M is 1 minus 8, that is minus 7, 0 plus 4, that is 4, and 3 is standard. And that's it. And that's it. This is the intersection point of the line and the plane. So this is not a very difficult method, as long as you understand how and why we are doing this. So yes, of course, we have to somehow solve a system, but the easiest solution is using one variable, one unknown only. That means parametric equations. Parametric equations in any situation are good exactly because of this. X, Y, Z coordinates depend on only one variable. They are not connected in perhaps a very direct manner in this kind of equations, but they still are using a single one and only one unknown number. Now the angle. So the vector S is, as we have already seen, minus 2, 1, 0. The vector N is, as we see, 2, minus 3, 10. Now the angle, remember that the cosine of any angle between two vectors, cosine of angle between two vectors equals the scalar product, the dot product of these two vectors, divided by both these magnitudes. So divided by the product of magnitudes. And that's the angle between vectors. I'm writing alpha. I'm not using the same notation because the angle between two vectors is not necessarily the angle between two lines. It's not necessarily acute. But what we have to remember about time, about the line and the plane, is that it will be the sine of the angle that we are looking for, and it will be the absolute value of this. That's why I'm not writing even theta, because theta will be acute, but alpha could be accidentally obtuse. And so the sine would be the scalar product. So this is actually a good thing to do it separately. Many people just plop down some number, and I have no idea where they got it from. So in principle, we should do S times N equals minus 2 times 2 plus 1 times minus 3 plus 0 times 10. And then we see it's minus 4 minus 3 is minus 7. So for sine, we use plus 7. Remember, we had to use the absolute value, or I will write minus 7, but with this absolute value. It will become plus 7. And now we will have the two magnitudes. So the magnitude of the vector S, I saw people completely confusing vectors and magnitudes. They started writing vector is a number, the magnitude. So the vector magnitude is 2 square, that is 4, plus 1 square, plus 0 square, so the square root of 5. And the magnitude of n is square root of 2 square, plus 3 square, plus 10 square. So that's 113. So the sine is of the angle that we are actually looking for. The sine of this particular angle. So it's the sine because we are looking not between the two vectors, but between the line and the plane. And the absolute value, it has to be positive because the sine of an angle geometrically is positive. 7 over root 5 root 113. And I think, yes, there I have it. So I will erase this last line I wrote because now it's pretty obvious. So I'm erasing this last absolute values because everything is written in here. As you can see, I have written in the printed form already, I have written how to find the dot product, the scalar product, how to find the absolute values, and here we have this result. And it turns out that the angle phi is approximately 17 degrees. So this last part, of course, is using calculator. So this is generally how we do this in practice. Finding the intersection point is not so difficult as long as you set up the equation correctly and carefully. Just carefully. Carefully is the most important part. And finding the angle is not difficult either if you remember how to find the cosine of the angle between two vectors. And remember that actually we need to take the absolute value because the angle needs to be acute. And what was cosine now becomes the sine of the angle that we are looking for. The cosine of the angle between vectors, or the acute angle between the directions, is actually the sine of the angle that we are seeking. That's according to this picture. Now, distance from the point to line. Again, this was something that we had. We had it last time, but I told you that we will be actually finding the distance, looking at examples this time. So the method is, this is simply a quick run through one more time. We did it once on Monday when we went through this problem, when we went through this question. And now we will do it for a second time and with an example, of course. So how to find the distance from a point, and this is again the same wrong thing. I forgot to correct. I'm very, very sorry. This will be point x1, y1, z1. This, because this is not the same point x0, y0, z0. I thought to correct it, but after I finished the lecture, I was in a hurry because I had another class, so I forgot to make that correction. So what we do is, this is now M. Okay, let's rename this point 2. Let's call this point P. No, M is sorry. It's right. It's correct. All right. It's always a mess when I forget to correct my my problem, my mistypes and misthings. And in this case, I was not thinking when I was writing this. I was not really thinking when I was writing. I was absent-minded. So we find the equation for the plane. So what happens here? Suppose we have this line given by this equation, and we have this point with coordinates x1, y1, z1. What you should remember from Monday is that unfortunately, unlike the distance from point to plane and unlike the distance from point to line in 2 dimensions, in 3 dimensions, there's no formula for the distance from point to line. There's no formula. It might be possible to somehow write this formula, but it would be so messy and very difficult to remember and messy to write that it's simply not worth it. The formula is not really similar to the previous formulas. So we find an equation for the plane. In other words, we say, okay, so what if we had a plane passing through this point and perpendicular to this line? This means that the line intersects this plane somewhere. This line is perpendicular to the plane. That is, the direction vector of this line is the same as the normal vector of this plane. That's one thing. The second thing is that because the point M is in this plane and the intersection point P, let's say, is also in this plane, then the vector MP will be perpendicular to the line, to the normal vector. So MP is actually the distance. MP will actually be the distance. So what we do is we find the equation of the plane passing through point M and perpendicular to this line. That is easy to do. That is easy to do because, as I already noted, the normal vector of the plane is the same as the direction vector of the line. Back to white. Direction vector of the line is S. We can use the same vector for the normal vector for the plane. And so we know how to write an equation for a plane passing through a given point. Then we have a plane and a line. Find the intersection point, as we did just a little bit ago, using the parametric equations. That's the easiest way. When we have the intersection point P, then we simply find the distance, that is the length of the vector PM. Okay, let's try it. The line is given parametrically, which means the direction vector of this line is the vector of coefficients at t. So 1t means we have 1, minus 1t we have minus 1, 2t we have 2. Please do not be deceived by the reverse order. So sometimes you would have t plus 1, and sometimes you might have 3 minus 2t. Remember that the direction vector consists of the coefficients at t. And therefore, I have 1 minus 1, 2. I'm looking at the coefficients for the parameter t. So this is the direction vector. The point for this line would be 1, 2, 0, the point through which this line passes. At the moment, we don't even need this other point through which the line passes. So what we have is a line with this direction vector S. Again, I would say it's always useful to make a sketch. No matter how many times we do this during practice, it actually is a very good idea to do a sketch. This is the vector S. So the point L is somewhere, the point of the line is somewhere, but we are not really interested in it. And then we have this point M somewhere. I will make it red. The point M that has coordinates 2, minus 1, 3. We need to find this distance. So what we do is, evidently, we will construct the plane. That is passing through the point M, passes through this red point, and is perpendicular to the line. And so, of course, there somewhere we will find this intersection point P. So this will be the correct distance. This is the intersection point, and this will be the distance. So what we do is, of course, the normal vector for the line, for the plane, will be the same, 1, minus 1, 2. That is already, without calculations, we simply copy it. The point coordinates we already have. So we write the direction, the equation of the plane. So plane perpendicular to the line. We are writing down the comments, and actually this is something again that in many cases is missing. Many people do write down the comments for solutions. That is very good. I'm glad for that. But in principle, you should write down, you should explain what is it that you are doing there. Otherwise, you simply write down some numbers, some calculations, and I have no idea what you are doing there, especially if the calculations are wrong. And so we have 1 times x minus 2 minus 1 times y plus 1 plus 2 times z minus 3 equals 0. See that 1 minus 1, 2 is this vector, 1 minus 1, 2, the coefficients a, b, c. The coordinates of the point M go in for x1, y1, z1. And so we can simplify the equation of this plane. So it will be x minus y plus 2z, and then we have minus 2 plus 1, minus 2 minus 1 is minus 3, and minus 3 minus 6 is minus 9 equals 0. That is the equation of this plane. Now we have the parametric equations of that line. To find the intersection point, we must now combine plane and line. Plane intersects line. So we put the parameters, parametric expressions t plus 1 minus t plus 2 and 2t into this. So instead of x, we put t plus 1 minus, instead of y, we put minus t plus 2 plus 2z. Instead of z, we put 2t, and of course minus 9, which should not be forgotten. So we have t plus 1 plus t minus 2 plus 4t minus 9 is 0. t, and 4t is 6t. And here we have 1 minus 2 minus 9. Looks like this is, on the other side, it's 10. This is 10. Now I remember, I guess I had the not the very nice value, 10 over 6 or 5 over 3, the t value. So the point P would have coordinates. Now, if I put t into the equation of the line, 5/3, there is 1 and 2/3, plus 1 is 2 and 2/3. Or I can write it in the form of improper fraction. 5/3 plus 3/3 is 8 over 3. Now minus 2 plus minus t plus 2, 6/3 minus 5/3 is 1/3. And finally 2 times t is 10 over 3. Or if we like, 3 and 1/3. So not the nicest possible coordinates, but still a possibility is there. And so the last step would be finding the distance. The last step would be the vector MP or PM, whichever we prefer to do. Let's do MP. The vector MP would be, basically the vector MP is 8/3, so 2 and 2/3 minus m coordinates minus 2 is simply again 2/3. 1/3 minus -1 is 1 and a third, and 3 and 1/3 minus 3 is simply 1/3. Or we can say it is 1/3 of 2, 4, 1. And then we would take the length of this vector, that is, we could find the length of the vector 2, 4, 1, and of course divide by 3, because MP is 1/3 of this vector. So the distance MP would be 1/3 of square root 2 square plus 4 square plus 1 square. That is 21. So it is 1/3 square root 21. Root 21 divided by 3 is the distance. So not very nice numbers, but it is doable. So in principle, what matters is how we go about this. The numbers in the end are not so important at the moment as understanding what we do. We find the equation for the special plane. We find the intersection point of our line and this plane. And then we actually say, okay, this now will be the distance between the given point and the point we found. That will be the distance. So we simply have to find the distance between 2 points, or we can find it as the length of the vector. And now some exercises. Intersection point of the line and the plane. One more time. So the basic exercises, let me just check. So right now we should be finishing in a few minutes, but because we started late, I will endeavor to work till 10. So 18 minutes more. So we will finish at 10. That will give us a smaller, shorter break before elementary mathematics. But I can move that a little bit down as well, so that you do get your break and I get my break. So I'm just checking how many exercises we have, and which ones are the important ones to manage by all means. Intersection point, angle between line plane, intersection point line and plane YZ. That will be decent. We had something similar. Actually, we can skip this. Equations through one point perpendicular to this line, that I should do. That is something I should do. I will mark this definitely. So we can skip the previous one. Line, angle between line and plane. Basically, we need to find a vector. We may skip, we may or may not, but this is something we must do by all means. I would like to do this. Canonical equations of line perpendicular to plane. That would again be very simple. I think we can start with this, or we can skip this. Symmetrical. Oh yes, this is important. And equation of the plane containing the two lines. And what is the situation? Okay, yes, these are the ones that we need. Prove that the lines intersect. Prove that the lines intersect. So we need at least to have a look at these. Equation passing through that point and the line, maybe. All right, so now I see these are the things that we need to do, which means I will probably skip this. Finding the intersection point of the line and the plane, remember that best of all, express this, okay. Best of all, express this using the parametric equations. As we agreed, it's best to express this parametrically. Otherwise, you have a system of 3 equations. These equations need to be simplified, although it is possible. Yes, you could take one equation, just simplify it to the classical standard form. The second equation, just remember to simplify it. and the third equation, which is the equation of the plane. So you would have three linear equations, a system of three linear equations. After simplifying, you can solve it using matrix methods. This is also possible, yes. But the better way would be, of course, writing x is minus 3 plus 2t, y is 4 minus 3t, z is 2 plus 2t. Then take these, put them into the equation of the plane, find the value of t, and put the t back into the equation of the line to find the coordinates of the point. I'm simply going through, yes, in the e-studies, yes, e-learning. That's if you can go there. So yes, e-learning, if you go to that page, you can find the link. That's a big problem. I know that we have this problem today with the servers, because Ortus is one portal, one website, and e-learning is another website. They are connected, but today we cannot get into e-learning from Ortus. That's the problem today. That's why we've had difficulties. Okay. Uh, and now the angle between line and plane basically means we need to find the direction vector of the line. We do not need the equation of the line. We only need the direction vector. So if you can find the direction vector mn, you have the normal vector from the line, and you find the angle. Just remember, it was the sign that you found. You find like finding the angle between vectors, but remember that you need the absolute value on this, and it will be the sine of the angle between, because it's between line and plane. I am not staying with this because there are more important exercises for us to do. Intersection point of the line and plane YZ. In the plane YZ, the x value is 0 throughout this plane. So if you put x is 0 into the system, you get a system of two equations, two variables y and z. Oh, they have added it. Oh, excellent. So they are aware. Evidently, the IT department is aware of the problem.
No, miss. The thing is, I emailed them and they actually sent me the link, but I don't know if they added them. So I just sent them the email.
Okay. So see, this link e-studies excellent. At least they know the problem. They are aware of the problem. They can work on it. Very good. Excellent. This is very good. This is where we go to find our elementary mathematics. Great. And so if we put x equals to 0 into the intersection point, into the equations of the line, and see, this is the crazy type of equations. Remember, the equations of a line given by two planes, but we do not have to worry about the direction in this case, because we simply, on the plane, we know that on the plane yz, x is 0, we simply plop this into the equations of the line, and we get a smaller system only with y and z, and we can solve that and find the remaining coordinates. But the important part is, of course, again, the same thing, perpendicular to the line. The reason why I wanted this is that the line is again given by this crazy set of equations. That is not the canonical equation, not the canonical equations, actually plural, but by two planes. This was the situation when we had the line is actually described as the intersection of two planes, like this. And we need to find the equation of a third plane, which is perpendicular to the line, this line. That is, it has to be perpendicular to these two planes also. So we need to find a third plane that is perpendicular to these two, which means it is evidently its normal vector is the same as the direction vector of this line, the intersection line of the first two planes. Yes, a picture is necessary. You should sketch. You should sketch. You should sketch this. And then you understand very clearly that S for the line will be the normal vector of the new plane. That is, we have to find the direction of this line, which is the vector product, the cross product of the two normal vectors. And now this is the thing with ijk, where we actually find the normal vector as the vector product. As many of you wrote in the vector test, I, j, k. Then we have the first normal vector 1, 2, 1. But the thing is, the first normal vector is 1, 2, 1. The second normal vector, be very careful. What we see is y is missing. So the second normal vector is not 3 minus 2, 9. The second normal vector is 3, 0, minus 2. Very, very careful with this kind of situation. It's so easy to get the normal vector wrong, especially if one of the variables is missing. And so we write 3, 0, minus 2. And now we have I times minus 4 minus 0, that would be, so it's minus 4, minus j. Remember before j we had a minus. Minus 2 minus 3 is minus 5, plus k times 0 minus 6, that's minus 6. So this is minus 4 plus 5 minus 6. That is the direction vector of this intersection line, of this line that we are looking for, but it is also the normal vector of the plane that we are seeking. So the point M is somewhere there. So basically this is A, B, C. This is the normal vector for our plane. So we can now write minus 4 times x minus 3 plus 5 times y plus 1 minus 6 times z minus 4 equals 0. So 3 minus 1, 4 are the coordinates, of course, of the point M. And minus 4, 5, minus 6 are the coordinates of the normal vector, which just happens to be the direction vector of this line. Again, I'm absolutely not interested in the equation in any other form. I don't need the canonical equations of this line. I only need the vector, because I only need the direction to know that it's perpendicular. And so, of course, we have minus 4x plus 5y minus 6z, and then we have 12 plus 5 is 17 plus 24 is 41 equals 0. And then, okay, 2, 1, 0, let's try it. 2, 1, 0. We will have minus 8 plus 5 minus 0 plus 41. So, of course, the answer is no. The point 210 does not belong to this plane. So this kind of thing, I would very strongly advise you to sketch. I know that sketching three-dimensional things is not the simplest, not the easiest thing to do, but basically it is necessary, at least to some extent, so that you understand the situation. So if you have this situation of 2 planes or 3 planes, it's very good if you have 2 planes intersecting through a line to sketch them like this, like an open book. Like an open book, even perhaps even like this. If you sketch them as an open book, you see, okay, that's two planes intersect through a line, and now we are making the next line, like an open book set on a table. This is the line, this is the plane, this is the normal vector, and things become easier to understand, hopefully. Canonical equation passing through the point perpendicular to the plane, we already know that this would be 1 minus 3, 1 would be the direction vector because the line has to be perpendicular to the plane, so that should be easy enough. Now, finding the point symmetrical. This is the one thing I want to do, and then the rest, yeah, well, yes, today we are short of time. That's a huge pity. I will try to do one more after this. I'm sorry about the delay, but it's nobody's fault. Something technically went wrong there. Okay, the plane having this equation, then we have a point A, and we need to find the point symmetrical. We did this with the line. We had an exercise like this with the line in plane, in 2 dimensions. We had something similar. So what we need is, we need to find a line perpendicular to this plane. The symmetrical point will be evidently this one, and this is the intersection point. So what happens there is we need this perpendicular line, and we need to have this same distance, the equal distance. Then we can talk about symmetry. Here. And so we need, evidently, first of all, we need equation of the line AB. So the thing is, yes, we see that sketching is necessary. Line AB perpendicular to the plane. So that would be point, we have a point, we have the direction vector. So the direction vector will be 3 minus 1, 4. The point is given. So the equation of this line, and I will write it in the parametric form already. Why? Because we need to find that intersection. We need to find that intersection. Unfortunately, yes, we need it. So I'm writing this equation of the line AB in the parametric form. So X is, Y is, Z is, the point through which it passes is 2, 4, minus 3, and now the parameter plus 3t minus 1t plus 4t. The parametric equation. This is the parametric equation. Now, to find the intersection point, this was the first part. Next, we find the intersection point P, the intersection point. So we put these parametric expressions into the plane. 3 times 2 plus 3t minus 1 times 4 minus t plus 4 times minus 3 plus 4t. Don't forget, minus 16 equals 0. So we have 3, okay, let's see, 6 plus 9t minus 4 plus t minus 12 plus 16t minus 16 equals 0. 9, 1, 16, that's 26t. Now here we have minus, so minus 16 is minus 32. Minus 32 plus 6 is minus 26. So t is 1 for the point P. So we can say that the intersection point P is, it has coordinates. When t is 1, it would be 5. 4 minus 1, it would be 3. And minus 3 plus 4 is 1. That's the intersection point P. And now we have basically 2 options how to find the point B. How to find the point B? Option one is P is the midpoint of AB. That means the coordinates of P are the average values of the coordinates of A and B. So if the B has coordinates now X, Y, Z, then the coordinates of P being midpoint of AB are the average values. That much many people actually remembered how to find the midpoint. That would be A, that is 2 plus unknown X divided by 2. That would be Y value for A, 4 plus unknown Y divided by 2, and minus 3 plus unknown Z divided by 2. The midpoint of the segment AB, where B coordinates are unknown, is P, whose coordinates we know, 5, 3, 1. So this means that X is 10 divided by 2, X is 8. To get 3, we need 6 divided by 2, so Y is 2. And to get 1, we need 2 divided by 2, so Z is evidently 5. So the point B has coordinates 8, 2, 5. That's first option. One option of how to find this symmetrical point. The other option is if P has the T value equal to 1. Now this is something comparatively interesting. Again, let's take something in different color. Let's take yellow, brighter yellow. If T is 1 for the point P, that is, we need to take one direction vector, one step from A to P, right? Because T simply tells me how many steps of vector S I need to take from A. Remember that we had A equal A plus T times vector S, direction vector for the line. That means T tells me how many steps from the point A I need to take to get to P. So if I need to take one step from A to P, then from A to B, I need to take double that. I need to take 2 steps. So option 2 would be if T is 1 for P, then for B, the T value has to be, for B, the T value has to be 2 times 1, twice that, because we take one step from A to P, but 2 such steps from A to B along the same line. And so for the point B, now I apply T value equal to 2. That is 2 plus 6 is 8. 4 minus 2 is 2. And minus 3 plus 8 is 5. See, the same point, the same value. It's up to you which method you use. I like both of them. Both of them are interesting enough. Actually, the midpoint makes sense because it is based on our understanding of geometrically what it means. The second option is interesting because we understand the meaning of the parameter t. The second method actually tells me that you understand that to get from A to P, if we need one step from A to P, like t is 1 or maybe t is 3, then we need 2 times more steps to get from A to B. Understanding of symmetry again. Okay, let's see. Equation of plane containing the 2 lines. Okay, just the strategy. We have 2 lines. That means we actually have notice these lines, by the way. They are parallel. They are parallel lines. So 2 parallel lines, and we need to find the equation for this plane. That is, we need to find the normal vector because we can use any point. I know that on one line, the point is 0, 1, minus 2, that is from this, 0, 1, minus 2, and the point on the second line is actually minus 2, minus 1, 3, that is from these, from x 0, y0, z0 on the second line. And we know one vector in this line, in this plane. So this is a little bit about thinking. This is a little bit about thinking, not doing things mechanically. We know the direction vector of these two lines. We know this vector already. This vector is there. For both lines the same. We need one more vector. To get the normal vector, we need this, remember, vector product. So perhaps we should take this as another vector in that line. It doesn't matter which way it goes, but between these 2 points. So we have 1 point on one line, 0, 1, 1, minus 2. We have the point B on the other line, minus 2, minus 1, 3. And we would say, okay, the vector AB is in the plane. The vector AB is in the plane. And then, okay, it doesn't matter which way it goes. And then the other vector, the vector S, which is 4, minus 2, 0, is also in the plane. So we can get the normal vector because it has to be perpendicular to these two. We can get the normal vector of the line as AB cross product C, because this is the perpendicular vector to both of them. Again, you see, if you sketch and if you think a little bit of how the sketching goes on, what we actually have and what we can have, you can, in fact, figure out this connection. All right, guys, it's almost time to start elementary mathematics. We will start it at 10:30 so that you do get some break. We will start elementary mathematics at 10:30. And for the unit test 3 for vectors, we will do that on Monday after the spring break. So those of you who are not taking elementary mathematics, enjoy your spring break. I will see you in a bit less than 2 weeks, in 12 days. And that's the day when we will have this analytic geometry unit test. Please do some revision. It will contain elements of curves in the plane, lines in the plane, and lines and planes in 3 dimensions as well. So please do the revision. The exercises are there in the files. The answers to the exercises are in the files. If you have some questions about mathematics, you are welcome to email me. As soon as I have an opportunity, I will try. So if you have questions, mathematical questions, why is this, or how do I find this equation from that equation or something, or if you have a specific question about any of the exercises in the files, just email me and tell me which. Elementary mathematics will be now. Elementary mathematics will be now, and elementary mathematics test will also be now. And the home assignment, as soon as I finish elementary mathematics, I will post it.
Miss, for the marks for unit test 2.
Yes.
It's not published yet, right?
Oh no, they are. You sent me by email, right?
Yes.
Because you sent me by email. I think I did not put those marks in Artus. I did the marks. Automatically. They could be released. Those that I marked online. I see. I know the problem now. Yes. Okay. Thank you for reminding me. I will put them in there.
Okay. Thank you, Miss.
Okay. So basically, because of all this situation, evidently, the retake of the vector test will also need to be postponed for after the break. So you have more time for revision, more time to do things, have a bit of rest. And so elementary mathematics. We will start at 12:30. You have 20 minutes. We will do about 40 minutes new material and 40 minutes the test afterwards, the second elementary mathematics test. All right. So for some of you, I say goodbye for 12 days. And some others of you, I will still be talking to in 20 minutes.
Bye, miss. Thank you. Bye.
Bye.
Happy holiday.